Hello, my friends. Welcome to Origins. My name is Donn Chapman. It's my privilege to be your host. We like to say that Origins is a forum where we take the evidence of science and use it to validate the truth of creation. Our guest today is Dr. Larry Vardiman. Dr. Vardiman, how good it is to have you here with us.
Thank you, Don. I'm glad to be here.
Now, you are the coordinator of the RATE group.
Right. The RATE project is radioisotopes in the age of the Earth, and I was kind of the organizer of it and the administrator.
We're going to talk about helium today.
That's right.
But we're not going to talk about blowing up balloons for birthday parties.
No, we're going to talk about helium in rocks. Helium is one of the byproducts of uranium decay. Uranium is a heavy element that breaks down into lead, and it also produces helium at the same time. The uranium is what we call the parent element, and the lead that it's produced and the helium are the daughter elements. And so nobody's ever looked at the measurement of helium in dating rocks, but we've done that and found that it's completely different than if you looked at the lead that is produced in the rocks. And this really addresses what we call the icon of evolution, and we are actually coming up with alternative ages for the age of the Earth, which actually fit into the Bible. And the first one we want to talk about today is helium diffusion rates.
All right.
This helium that's created in the rock by the decay of uranium becomes an alternative dating method or a clock for estimating how old the rocks are. Before I get into that in detail, let me just give you a few of the basic assumptions for radioisotope dating. Radioisotope dating is the primary method for dating rocks, but it has some basic assumptions in it that have to be met. And for this situation, one or more of these may not be valid. The three basic assumptions are that there is no initial concentration of the daughter elements. In other words, if you're going to have a clock, you have to know where you start from. And the assumption is you start from zero, and however much you have, whether it's lead or helium, that tells you how long the clock has been running.
So there can't be helium or lead there at the beginning?
That's right.
Okay.
Or if there is there, you had to know how much there was,
Right.
but we have no way of knowing that.
Right.
So you assume that there's none there. The second assumption is that there's a constant decay rate of the uranium into lead and helium. Now, we can measure the rate at which uranium decays today, but we just assume it's always been that way. Now, those of us on the RATE project assume, like the conventional scientific community does, that that's been the case. In fact, we figured that that would be the hardest assumption to overthrow, but the results of this experiment actually dealt with that particular assumption and found out it wasn't true. The third one is that the system that we're looking at, it has to be closed. Now, what that means is that the amount of uranium that's there to start with has to be the same throughout the process.
Sure. And
that there's no additional uranium added to the system or taken away, or there's no helium or lead added or removed from the system by any other process than the decay of uranium into lead and helium. Now, that also is a very difficult assumption to be able to demonstrate, and there may be some, that in fact was the assumption we thought would be the biggest one to deal with, but the constant decay rate was really what came out in our results. When we started the RATE experiment, RATE stands for radioisotopes in the age of the Earth. When we started this experiment, we spent 3 years understanding what we were going to do in the major part of the project. And then we spent 5 years doing the experimental phase or the research phase. And at the end of that first phase, we had a set of questions that we said we were going to try to answer in the research phase. These are the basic questions. We had already come to the conclusion that the process of decay had to have been accelerated in some way. And we were going to try to see if we could demonstrate that. So our first hypothesis was that accelerated decay has occurred during creation, at the curse, and or during the flood, the Genesis flood we're talking about. A second hypothesis was that some daughter elements may have been primordial. That means that some of them were there to start with. For example, some of the lead, we in our experiment found that we could explain most of the lead, but some of it had to have been there in the original creation. We couldn't explain it all. And finally, we made the hypothesis that radioactive processes have produced evidence of accelerated decay. Now, we weren't sure we were going to be able to demonstrate that, but through the experiment, we actually were able to show that. And that's what was really exciting about this project.
Well, share with us what you've discovered.
Okay, let me start off and give you a little bit of background to how we did some of the experimentation. We did a lot of this work in our own laboratory, preparing the samples that we were going to send off. And I might say that we did the experimentation by using conventional laboratory work. And the reason we did that was it was going to be very expensive for us to set up our own laboratories for a whole bunch of different type of analyses. These labs cost hundreds of thousands of dollars each, and you have to have a technician who's well trained, and the lab has to have been established for many years. We didn't have the time or the money to do that kind of work. But more importantly was that most people would not believe the results if we did it in our own lab. So we sent these off to conventional labs, had them do the analysis, and then we did the interpretation of the data that we got back.
Which gives you a great level of credibility.
That's exactly right.
Right.
So we went out into the field and collected the rock samples, brought them back into our laboratory and sliced them up and ground them up, and then separated the various elements in them. Turns out that rocks have minerals embedded in them. In fact, the rock that we were dealing with most in this project was granite. You're familiar with granite. It's kind of a white-looking rock with black specks in it. The black specks are what's called biotite. It's a type of mica. It's kind of a little shiny surface on it. And these little zircon crystals are what we were dealing with. But we had to separate them out, so we broke the rock into pieces with a big hammer and in an iron pestle and mortar here, ground them all up as fine as we could get, and then separated the minerals in them. And you could either separate them by sifting them through a sieve, or you could pick them out under a microscope with the tweezers, which is really tedious, or you could put them in a liquid that's very heavy, not water. Water has a relatively low density, and some of these minerals are 3 or 4 times as dense as water, so we had to have liquids that were very, very dense, and then the lighter minerals would float to the top and the heavier ones would sink to the bottom. We were able to separate minerals that way and then filter them out. So we did quite a bit of that in our laboratory and then sent them off to the general laboratory to do the experiment. And one of the main things we were doing with the helium diffusion experiment was finding out how much helium were in these rocks and how fast that helium was escaping out of the rock. For example, if you have children and they've had helium-filled balloons and they tie the balloon under the end of their bed at night, they wake up the next morning and the helium has escaped out of the rubber in the balloon and the balloon is kind of collapsing down on the floor.
Right.
The same thing happens to rocks, but it goes on much more slowly. The helium will actually escape out of these. Now, the bottom line result we found from these experiments, I'll just state this up front and then we'll talk a little bit more about it, was that the helium diffusion work we did indicated that the 1.5 billion years, the equivalent of 1.5 billion years of radioactive decay, nuclear decay, actually occurred between 4,000 and 8,000 years ago. In other words, we think that this process started, much of the helium is still in the rocks, but it's been going on for, the best estimate, 6,000 years.
Yeah.
That is the number we believe from a literal understanding of Scripture when God created the earth. Well, let me tell you a little bit more about the inside part of the granite. Inside the granite rock itself is these biotite flakes, and in the biotite is these little zircon crystals that you'll see here. These zircon crystals are very, very small. You really can't see them. They're on the order of 100 microns or so, which is about the diameter of a hair on your head.
Mercy.
And in these little zircon crystals, embedded in the granite, is the uranium and thorium, which is radioactive. So the little crystal is kind of like a little capsule of radioactive material. The uranium is decaying. It decays and produces lead within that zircon crystal, and the helium is in there, and the helium has to escape out of that zircon crystal. These zircon crystals don't melt except at very high temperatures, and they can actually go through a volcano and not be melted. The magma, all the rock around them can melt, and the zircons are still there, so it can go through a lot of earth processes and still be maintained. Here's a picture of some of these in a little bit closer detail. This is the kind of crystals, they take various sizes and shapes, but basically they're on the order of 100 microns. I said very, very small, and they tend to have facets on them. Here's one of these crystals, and you can see it has little flat surfaces on it. Very, very interesting featured type crystal. Donn, here's a graph that shows how uranium decays into lead. The uranium that we find in our zircons starts off, and it starts as a uranium-238 atom, and it results in lead, but it also produces helium along the way. There's a decay chain of a whole bunch of nuclear processes that start between its uranium turning into lead, and in the process it produces 8 helium atoms. Actually, it produces alpha particles. Now, these alpha particles are the core of a helium atom. It's got 2 neutrons and 2 protons with no electrons, and it shoots out in all directions, and as it goes throughout the crystal, it produces damage in the crystal and then picks up electrons and becomes a helium atom. So the helium is trapped in that crystal after it's decayed. Here's an atom of uranium with all the electrons running around it, and it shoots out these alpha particles. There's 2 neutrons and 2 protons, and then it collects electrons and becomes a helium. That continues to do that. All throughout the life of the crystal, it produces all this product. If you take a rock as a whole, you can see this process going on, and it's actually kicking out helium. Now here's your alpha particles with the electrons around them. Those are helium atoms. So the rock is actually pressing out, or the helium is escaping out of the rock in all directions, but it takes a fairly sizable amount of time for that to occur. If it turns out if the rocks were 1 billion years old or so, all that helium would have already escaped. And when we went and collected the rocks, we find that the helium is still in the rocks, and we sent the rock samples to the lab to find out how fast it's escaping, and we were able to actually calculate the age of the Earth from how much helium is there and how fast it's escaping.
If they were really old, there wouldn't be any helium there at all.
That's right.
Okay.
But we found up to 50% of the helium that's decayed still in those rocks.
Still there. And that's a new finding, isn't it?
That's a brand new finding, and it's very controversial. We've presented this to the scientific community already, and they are astounded by it, and they're really scratching their heads over this.
You haven't really had a lot of response other than, huh?
Well, that's right. We presented this to the American Geophysical Union meeting in San Francisco in 2003, and we had about 400 specialists in this field come by and talk to us. They were really puzzled by it, and they've gone back to their labs, and some of them are working on this problem themselves now.
But it's really important that we point out that they're not doubting that the helium is there. They're trying to figure out the significance of it. Isn't that
yes,
right?
And how it's... Well,
that's a very different question. Absolutely, we're positive the helium's there.
There's no question about that, and
yes.
We're going to talk about that a little bit more after the break.
Okay.
But what's really puzzling them, they've spent most of their career looking at the lead, not at the helium.
Yeah. Right, that's right. And the dating has always been based on the lead instead of the helium.
That's exactly right.
But they're telling us 2 entirely different stories. The lead would give you one date and the helium an entirely different date.
That's right. The lead gives you a date of about 1.5 billion years, 1.5 billion years, and the helium, it turns out it's on the order of thousands. That's why we called it one of our books, Thousands, Not Billions.
Now we've got to take a break, and when we come back, we're going to have to deal with this dichotomy of results and how we justify that, or how we explain it, or what we think's going on. We'll be right back. You won't want to miss the conclusion. Stay with us.
Creation versus evolution. You weigh the evidence. A global flood, evidence pours in. 20th century geologists taught the familiar maxim, the present is the key to the past. But now that catastrophic processes are widely used to describe the strata record, 21st century geologists are discovering that marine flood sedimentation is the key to the past. Geological strata and their marine fossils provide critical evidence that the oceans once covered the entire planet. Widespread strata blankets are leading geologists to construct a global flood model for Earth history. Today's guest on Origins, Dr. Larry Vardiman, is chairman of the Department of Astrogeophysics at the Institute for Creation Research's Graduate School. Through his ongoing research in atmospheric science, Dr. Vardiman has contributed much to the field of creation science. He also led the RATE team, a research project examining the age of the Earth. This has been documented in the DVD, Thousands, Not Billions. For more information, contact the Institute for Creation Research, 1806 Royal Lane, Dallas, Texas, 75229, or call 1-800-337-0375. or visit the website www.icr.org.
We're back with Dr. Larry Vardiman, and we're talking about the discoveries by the rate group, and today we're talking about the helium that we're discovering in rocks, and this was something new and kind of earth-shattering to the scientific community. You have a chart there, Dr. Vardiman. Help us understand what that's about.
Well, I want to tell you a little bit more about the samples that we used to come to the conclusions we did. We obtained a core of granite from a drilling that was done in New Mexico by the Los Alamos National Laboratories. They were looking for geothermal sites, looking for steam that they could use to produce energy. And in this core, this site, they pulled out a core all the way down to over 12,000 feet down in the ground. And we had access to those cores and were able to sample them for the zircons in them. And in those zircons, look for the amount of helium. This table that you see here had samples from the top. Sample number 1 is near the top in meters. That's about 1,000 meters, which would be about 3,000 feet down in the ground, at a temperature of a little over 100 degrees centigrade, which is about the boiling point of water. And in that sample, we found that 58% of the helium was still there in the zircons that would have been released in 1.5 billion years, the equivalent of 1.5 billion years of decay. Now, it changed as we went down in the core, all the way down to almost 4,000 meters down, which is about 12,000 feet down in the rock. We found a temperature almost 300 degrees centigrade, much, much hotter, and there was only 0.1% of the amount of helium left there. Now, the reason for that is the hotter the rock is, the faster the helium is going to escape out. And there's physical laws that determine that. But the surprise to us was how much helium was still in the rocks at the colder temperatures. We then took this and put it into a graph that looks like the following. And now this is a bit of a busy graph, so let me describe it in a little bit of detail. The vertical axis is what's called diffusivity. And this was determined from the rock samples that we had by taking the amount of helium we found in the rock and calculating over what period of time we assumed that this helium had diffused out of the rock and how much was still there, and plotted that. The horizontal axis on this graph is temperature. Now, it's plotted backwards from what you would normally think of. The cold temperature is to the right, and the warm temperature is to the left. Now, up at the near the top, we plotted some data that we obtained from the core as a function of temperature, and we found that the measurement in the blue dots that you see there indicate that this would be the relationship between how much helium would diffuse, how fast it would diffuse. The diffusivity on the left side of the graph there is a measure of how fast it diffuses out. And that's a logarithmic scale, by the way. It's not linear, so it goes up exponentially. It's a very, very rapidly increasing value. But we plotted that data, and then we put on that same graph an estimate if it had happened in 1.5 billion years and a 6,000 year period of time, what we would expect it to do. And
that's the two models.
That's the two models you see there. At the bottom is the uniformitarian model, which was the 1.5 billion years. That meant if the helium that we find in the rocks was diffused over that 1.5 billion years, it would have to be a very, very slow rate of escape or diffusion.
Right.
And therefore, it's down near the bottom of the graph. If it happened over 6,000 years, which is our creation model, then it would happen a lot faster. We put that data on there, the first set of data, and put the model together and reported that in our first report, saying this is what we would expect the difference to be. When we sent the data off to the lab to actually get the measured diffusion rates, we then plotted this on the graph after we had projected what it would be, and the blue dots are what showed up on the line there, and it matched up with the creation model.
So the data perfectly fits the creation model. I don't see any blue dots down there in the uniformitarian model.
That's right, and there's over 100,000 times difference between those two models. So
the difference between billions and thousands.
That's exactly
Sure.
right. And we anticipated that we would have the model be confirmed by the data we went out to the field to get, but we said this ahead of time. This is one of the things you do in science. You make a prediction,
yes,
and then when you collect the data and compare it with your prediction, or a hypothesis as
yes,
we called
that's
it,
right,
it fit the creation model right to a T.
That had to be really exciting.
Oh, our scientist, Dr. Russell Humphreys, who did this work, was just astounded. In his 30 or 40 years of research, he had never had the data come out that close to his prediction. He was just thrilled with it.
Would you use the word irrefutable with this?
I think so. I mean, it's incredible that it came out so well. Now, there's obviously going to be some criticism of this. People have had different ideas as to why that would be. In fact, we've had probably a half a dozen different attempts to refute this, and Dr. Humphreys has been successful in turning all those criticisms aside.
That's exciting.
So it's really come out well. Now, we're able to turn that data around also, and since what we were doing was measuring the diffusivity and measuring how much helium was actually there, if you turn the equation around, you can project what the age of the Earth actually is. And we came out with an estimate of 6,000 plus or minus 2,000 years.
And I like the way you guys say it. It's thousands versus billions. And so, you know, we're not going to quibble over 1,000 years. We're seeing two whole different worldviews that are represented here, and the evidence is supporting the creation model. I think that's so exciting.
Now, maybe it'll help our viewers to be able to see the difference here between this long age idea of billions of years and thousands of years by taking two sundials. On the left, we have the nuclear decay sundial that would result in 1.5 billion years. And up on the top of this clock is uranium decaying into lead. And there's a little lever there, it was highlighted, that basically we believe God turned the lever on this during the Genesis flood. Over on the right is helium. When the uranium is decaying, it produces both lead and helium. You'll notice that it connects to the right sundial, and the helium is being put into the second sundial, and it's accumulated in the upper part of that like it's accumulated in the zircons. During the time that there was accelerated decay, which we think happened during the Genesis flood, there was a lot of lead produced and a lot of helium produced. And then at the end of the Genesis flood, when the accelerated decay was shut off, God kind of turned that dial and it slowed down to the rate that we have today. But yet the helium had accumulated during that period of time in the zircons, in granites. Although today the decay rate of uranium into lead is very slow, the helium is still there, slowly leaking out of the zircons, and we believe that that is a preferred method of estimating the age of the Earth.
Accelerated decay, I have a feeling, is going to become a very pertinent term in the origins debate in the years ahead.
I believe you're right. The uranium lead clock gave 1.5 billion years, and the helium clock gives us 6,000 years. So the two clocks were going on at the same time. We've just been looking at the wrong clock.
We've been looking at the wrong clock. I'm going to read this sentence again from the introduction of the Book of Conclusions. This is Volume 2 of Radioisotopes and the Age of the Earth, the report of the Rate Committee. And in the introduction, the final paragraph begins with this sentence. This book opens a new chapter in the origins controversy. Friends, there is going to be pushback on this. There are going to be evolutionists who are going to try to refute this exciting scientific finding by the RATE team. But I believe that God has kind of thrown a curveball here that is going to make this debate a whole new debate on a whole new playing field in the years ahead. Dr. Vardiman, you have given us a great service, you and your team, and we're so grateful. And I'm so grateful that you've been here to share it with our folks on Origins. So always remember that it's God's view He created you, and that should be your worldview too. Until next time, I hope you'll ponder this incredible stuff that we've learned today on Origins.
Thank you for watching this edition of Origins. If you'd like a copy of the PowerPoint information presented today, you can download a PDF file of program number 813 from our website at www.originstv.org. Or for a DVD of this series, send a $12 donation to cover shipping and handling and write to Origins Program number 813, Cornerstone Television, Wall, Pennsylvania 15148.
Origins is made possible by the faithful prayers and the financial support of you, our Cornerstone Television family.